In section 7.1, we learned about linear transformations, and one of the things we learned about them were some properties that were true about transformations. There we were only talking about linear transformations of vectors. So we were going from, for example, R2 to R3 or R7 to R5. And all of the things in my transformations, all of the inputs were vectors in Rn. So if I had u and v in R3, then the transformation of t of a vector v, for example, would result in a vector in sometimes the same and sometimes a different vector space, right? A different dimension. And the properties that we were told about at the time were the additivity property and the homogeneity property. The additivity property says you can either add two vectors together first, then transform them, or you can transform two individual vectors and then add the results, and you'll get the same thing. It's a little bit like saying addition is associative. It's not quite like that, but it's similar. Addition of real numbers is associative. So that is one of the properties we learned about in 7.1. Here's the other one. I can either scale a vector and then transform the scaled vector, or I can transform a vector and then scale the result, and I'll get the same thing. Well, the nice thing about this is that we're not stuck in working with real numbers here. We're not stuck working with Euclidean vector spaces. In property 7.2.1, the exact same two properties are listed and they are identical. The only difference is that u and v are not now necessarily vectors in Rn. In 7.1, a vector u was in a vector space called U, where U was equal to, for example, R3. I'll just say U is equal to Rn. But in 7.2, a vector V is in a vector space V, where V is equal to any vector space. It could be, for example, let's say the polynomials of degree n or less. It could be matrices that are 2 by 2. What else could it be? It could still be a vector, right? It could still be a vector in Rn. So now we have several choices from where to pull our vectors, right? We might be pulling from Rn as we did in 7.1, but we also might be pulling from some other vector space. But the nice thing about the property 7.2.1 is that those two properties still apply. There are actually a couple of other properties that are not listed in your textbook that I'm going to go ahead and list here. I'm not entirely sure what this one's called. We'll come back to that in a minute. But one of them is that the transformation of the zero vector is equal to the zero vector. Now, one of the things you have to keep in mind here is that because we could be in any space, right? The domain could be Rn, or it could be the set of all polynomials of degree 7, or it could be a 7 by 3 matrix, all 7 by 3 matrices, could be anything. And the codomain could also be anything, and they don't have to match. So I might be taking a zero vector here in, say, the set of all polynomials of degree 4 or less, and putting it into a 2 by 3 matrix, for example. But when I do that, the zero vector in the polynomial space, when transformed, spits out a zero vector in the matrix space that I've just described. Let's see if I can figure out a name for that one. One of the names that I found, it's not really a name, it's more of a description. The transformation T preserves the zero vector. So that if the zero vector is your input, then the zero vector will be your output. Even if the spaces, the domain and the codomain are different spaces. Another property that's listed in another textbook that I sometimes reference is that T of negative V is equal to negative T of V. But that's not really a new property, because if let me just do it. If this is a negative 1, right, then really all I'm doing is describing the homogeneity property using a very specific number, the number 1. R is a real number, Because we haven't specified the field, we're assuming that the field we're working with here is the real numbers. So if r can be any real number, then certainly it can be -1. So I don't need this property because it's actually already here, right? It's already described as it's the homogeneity property for a very specific value of r. Another one that this textbook, not your textbook, a different textbook gives is t of u minus, oh, my arrow in the wrong place there, u minus v is equal to the transformation of u minus the transformation of v. But there again, what I have is something of a linear combination here. We have it's like saying -1 times -v. And so I'm using the homogeneity property on this vector, right? And then I can say, I make that plus -1 times v plus -1 times the transformation. Make that negative a little bit bigger. And so then in that case, I really have a special case of the homogeneity property and the additivity property. And so again, I don't really need this property because it's already in the list. That description was for a very special case. So the only one that we've added here is the preservation of the zero vector. Okay, let's take a look at an example. Let's let the transformation t take a function of x and transform it by taking its derivative. So what we're going to do here is our input is a function and our output is going to be the derivative of that function. The first thing I'd like to do here is make sure that this is in fact a linear transformation. And to do that, we're going to check that the additivity property, the homogeneity property, and the preservation of the zero vector property all hold. So what I need is two vectors in my vector space. Let me also specify this is going to be over the real numbers. I need two vectors in my vector space, right? And what my inputs are functions. They could be any function. They could be exponential. They could be trigonometric. But I need two of them. So if I take the function f and g, then is it true that the transformation of f plus g is equal to, I'm checking this, so I don't know that it's an equality just yet. Is it true that that is the same as the transformation of f of x plus the transformation of g of x? And one too many parentheses there. By properties of differentiation, properties of the derivative, we know that is true because the derivative of the sum of two functions is equal to the sum, oops, my transformation notation there, is equal to the sum of the two derivatives. Okay, so that means that this property holds. Now notice that I've done this with generic functions. I have no idea what these functions are. I just know this to be true about derivatives. So I can check the property holds true. Now I'm going to do the same thing for the homogeneity property. Put a dotted line down here. Is it true that if I take the derivative, let me write the property first. That's what I did in the space above here. I want to check that the transformation of some real number times a function is equal to a real number times the transformation of the function. Is that true? Well, in this case, that would be like saying take the derivative of r times a function. And is that equal to r times the derivative of a function? And we know that that's true because of the, I don't even remember what this rule is called, but you can bring the constant out front, right? For example, if we had 3x squared and we wanted to take the derivative of that, we would say that that was equal to 3 times 2x, or 6x. So at bringing the constant out front. That's kind of a special case of the product rule. The product rule says that the derivative of this product is the first times the derivative of the second plus the second times the derivative of the first. But the first factor there is 3, so the derivative of that is 0, and that all goes away. So that's how we get 3 times 2x. Anyway, so that constant can get pulled out front. And so that's essentially what's going on here. I can pull the constant out front and then take the derivative. Okay, I've run out of room, so what shall I do? I think I'll erase this because we've pretty much examined everything there that we need. And I'll continue my dotted line along here. And all I need to check now is whether or not the transformation of the 0 vector in f of x is equal to the 0 vector when you take the derivative. Well, if what I'm doing is, I'll go back up to this generic version here, I'm plugging in the 0 vector in the vector space of functions, right? What I'm plugging in here is a function, right? What I'm plugging into my transformation is a function. I can take any algebraic function and plug it in here and transform it by taking its derivative. But what if what I plug in is the 0 vector in functions? In functions, what is the 0 vector? The answer is that it's 0. It's the real number 0. So I'd be taking the real number 0 and taking its derivative. And when I take the derivative of 0, I get 0. So I didn't check the second one off. This one holds true. And down here, I demonstrated that this one holds true. So that says that this transformation over the real numbers is, in fact, a transformation. This expression here is a linear transformation because all 3 of these properties has been preserved. Okay, I'm going to wait just a beat here so that if you wanted to stop the video and write some of this down, you could, but then I'm going to erase this screen. So in 5, 4, 3, 2, and now what I'm going to do is using the same transformation. I'm going to grab a highlighter here. I'm going to use this transformation, and I'm going to do a specific example. Let's let f of x, the wrong color pen, let's let f of x equal e to the x and g of x equal the sine of x. And I just want to perform these 3 properties, check these 3 properties on those 2 specific functions. So is it true that, I'm not going to bother with the vector notation at this point, is it true that the transformation of e to the x plus the sine of x is equal to the transformation of e to the x plus the transformation of the sine of x? The transformation, the derivative of this sum, right, is going to be, that's going to equal e to the x plus cosine of x. And on this side, I'm going to have the transformation of e to the x is e to the x. Here, I'm going to get the transformation of sine of x is cosine of x. And I'm adding them together. So that property holds true. Now, I'm doing exactly what I did before, but I did it in general terms the first time. Now I'm doing it in specific terms with 2 specific functions. For the next one, I think I'll use sine. So I'm going to check this second property, the homogeneity property, and that means that I need to check whether or not it's true that the transformation of, say, 3 the sine of x is equal to 3 times the transformation of the sine of x. Well, this one here is going to give me the derivative of 3 sine x, and this one here is going to give me 3 times the derivative of the sine of x. And of course, that's just 3 cosine x, and that's 3 times cosine x, and of course those two are equal. So the second property also holds. And the third one is not actually possible to do in this one because neither one of those functions is the zero function. I can plug 0 in for x, but that's not the point here. The point is that my vector, my input vector, which is a function, is either e to the x or sine of x for this specific example. The only zero vector in the space, in the vector space of functions is the number 0. So I can't check that here because I have two functions that are not the zero function. And again, I'm going to erase in 5, 4, 3, 2. All right, here's a different kind of example. Let's let T be a linear transformation from the vector space of 2 by 2 matrices to the same vector space. So the domain and the codomain are the same, but such that the following 4 statements are true. These 4 vectors are all 0 vectors except for in each one there's a 1 in a different position. So here I have row 1, column 1, row 1, column 2, row 2, column 1, and row 2, column 2. That's where my 1s are. And I've been asked to find the transformation of this vector here. So I'm going to start this one by rewriting the vector 1, 3, -1, 4 as 1, 0, 0, 0 plus 0, 3, 0, 0 plus 0, 0, -1, 0 plus 0, 0, 0, 4. And I can then take that and write it as 1, 0, 0, 0 plus 3 times 0, 1, 0, 0. You see where this is going? Let's just use minus there because I have a 1. It's just negative. 0, 0, 1, 0. And 4 times 0, 0, 0, 1. So that then is going to be equal to my pointer. This vector, when this is my input and I transform this input, what I get out is that. So when I put this vector, where am I? I put this vector in, I get this vector out. So my first term here is going to be 1, -1, 0, 2 plus 3 times what I get when I plug in the vector with the 1 in the row 1, column 2 position, and that's this one here. When I plug this into my transformation, I get this one out. So I have 0, 2, 1, 1. And then I'm going to have to go down here, minus, when I plug this vector in, I get this one out, and I'm just subtracting that vector, so I'm transforming that vector. My notation's a little bit weird here. I should have done this. The transformation of this vector is equal to the transformation of the sum of vectors, which is equal to, I got a little carried away, got ahead of myself, which is equal to the transformation of this collection of vectors. And now I'm actually doing the transformation, so I no longer need that notation. But now what I'm going to do is take this vector, subtracting this vector plugged in, and this vector plugged in gives me 1, 2, 0, 1. And then I'm going to add 4 times, what do I get when I plug in this vector, I get 3, negative 1, 1, 0. That's a 1. Now, of course, once again, I've run out of room. So making a reputation for myself here. I'm going to have, if I do the arithmetic here, I get 1, negative 1, 0, 2. Scale the next one by 3, 0, 6, 3, 3. Now I'm just doing vector arithmetic or matrix arithmetic, right? Minus 1, 0, 2, 1, plus scale this one by 4, you get 12, negative 4, 4, 0. And altogether, that's going to give me 1 plus 0 minus 1. So far, that's 0, plus 12. Tell you what, let me do this last step in a different color. I'm going to get 12 for that position. Then for row 1, column 2, I'm going to get negative 1 plus 6, which is 5, minus 0, so I'm still at 5, minus 4, so negative 9. Row 2, column 1, 0 plus 3 minus 2 plus 4, that's 1 plus 4, which is 5. And the last one is 2 plus 3 is 5, minus 1 is 4, plus 0. So the transformation of this matrix here, this vector, equals this matrix, this vector output.